Welcome to Science Snippets Fun Facts and Trivia. Today, we bring you, is the universe a simulation? Shocking evidence revealed. Chapter 1. Introduction. Are we living in a simulation? Section 1. The rise of simulation theory. Have you ever wondered if the world around you is real? What if everything you see, hear, and touch is just part of a highly advanced simulation? It may sound like a science fiction plot, but some of the world's greatest minds, scientists, philosophers, and even tech billionaires, are seriously considering this possibility. The idea that we might be living in a simulation isn't new. For decades, science fiction authors have explored the concept of artificial realities. From The Matrix to The Truman Show. But in recent years, this theory has moved beyond Hollywood and into the realm of serious scientific discussion. Researchers have started asking profound questions. Is our universe fundamentally different from a computer program? Are the laws of physics just the rules of a simulation? And most importantly, can we ever prove whether or not we are simulated? One of the main reasons the simulation hypothesis has gained popularity is the rapid advancement of technology. Just look at the progress of video games. In the span of a few decades, we've gone from simple pixelated graphics to hyper-realistic virtual worlds that are nearly indistinguishable from reality. If humans can create such immersive digital experiences today, what will we be capable of in 1,000 years? Could an advanced civilization have already reached the point where they can simulate entire universes, complete with conscious beings who don't even realize they are inside a program? This idea was famously proposed by philosopher Nick Bostrom in his 2003 paper, Are You Living in a Computer Simulation? He argued that if technological progress continues, future civilizations will eventually develop the ability to create simulations so advanced that the simulated beings inside them would be self-aware. If this is possible, then statistically speaking, it is far more likely that we are in a simulation rather than in the original real universe. At first, this might seem like an abstract philosophical question, but many scientists believe it has real scientific implications. If our universe is simulated, then there should be detectable clues, glitches in the system, mathematical patterns, or even computational limits in the way reality operates. In fact, some physicists believe they may have already found evidence that supports this idea. So, how did this theory become such a widely discussed topic? And what are the strongest arguments in favor of it? In the next sections, we'll explore the key thinkers behind this idea, the scientific evidence that may support it, and the mind-blowing consequences of discovering that our reality is not what it seems. Section 2. Key supporters: scientists and philosophers. If the idea that we live in a simulation sounds crazy, you might be surprised to learn that some of the world's leading thinkers take it very seriously. Scientists, philosophers, and even tech billionaires have weighed in on the topic. And many believe there's a real chance that our reality isn't what it seems. But who are these people? And why do they think we might be living in a simulation? One of the most influential figures behind this theory is Nick Bostrom, a Swedish philosopher at the University of Oxford. In 2003, he published a groundbreaking paper titled, Are You Living in a Computer Simulation? In it, he proposed 3 possibilities. 1. Civilizations never reach the level of technology required to create realistic simulations. 2. Civilizations reach this level, but choose not to run simulations of conscious beings. 3. Simulations are possible, and if they are, there would be far more simulated beings than real ones, meaning we are almost certainly living in a simulation. Bostrom argues that if the third option is true, the odds of us being in the real universe are astronomically low. His argument sparked widespread debate and was taken seriously by physicists, computer scientists, and even world leaders in technology. Elon Musk, CEO of Tesla and SpaceX, has famously stated that the odds of us not living in a simulation are 1 in billions. He compares our current progress in video game technology to what an advanced civilization might achieve if we can already create highly immersive virtual worlds today. Imagine what a civilization a million years ahead of us could do. According to Musk, it is almost inevitable that some advanced species has created a simulated reality. But it's not just philosophers and tech moguls who support this theory. Some physicists believe there's actual evidence. Neil deGrasse Tyson, a well-known astrophysicist, has said that the probability of us being in a simulation is better than 50-50. He argues that if another civilization had the ability to simulate entire universes, they could create countless simulated realities, making it much more likely that we are in one of those than in the original base reality. On the other hand, there are skeptics like theoretical physicist Sabine Hossenfelder, who argue that the simulation hypothesis is unfalsifiable. It cannot be tested or proven, making it more of a philosophical speculation than a scientific theory. Nonetheless, the debate continues, and as technology advances, scientists are beginning to explore ways to test this hypothesis. In the next section, we'll explore how this idea became so widely accepted, and how media, science fiction, and real-world technological advances have influenced public perception of the simulation theory. Section 3. Why this idea matters. At first, the idea that we live in a simulation might seem like nothing more than an interesting philosophical thought experiment. But what if this theory is true? What if our entire existence is part of an advanced computer program? If that were the case, it would fundamentally change the way we understand the universe, our purpose, and even the nature of consciousness itself. One of the biggest reasons why this theory matters is its potential impact on physics and cosmology. If we are in a simulation, then the fundamental laws of the universe, such as gravity, quantum mechanics, and the speed of light, might not be inherent properties of nature but rather programmed rules within a computational system. This could explain why certain physical constants seem finely tuned for life. Scientists have long wondered why the universe appears to be just right for human existence. If we are in a simulation, the answer might be simple: it was designed this way. The implications don't stop at physics. If reality is a simulation, then what does that say about consciousness? Are our thoughts and emotions real, or are they simply data being processed by an external system? Some researchers suggest that if we are in a simulation, our minds might be part of a larger network, perhaps even connected to a higher intelligence outside the simulation. This idea challenges traditional views on free will, identity, and what it means to be human. Beyond science and philosophy, the simulation theory also raises ethical and existential questions. If we are part of a simulation, who or what created it? Is there a purpose behind our existence? Or are we merely entertainment for a more advanced civilization? And if we ever discover that we are in a simulation, should we attempt to escape or simply accept our reality for what it is? Moreover, this theory has a psychological impact on those who take it seriously. Some people find comfort in the idea that life is a carefully designed simulation, while others feel disturbed by the thought that their actions might be predetermined by an unseen programmer. If the simulation hypothesis were proven true, it could lead to a shift in human consciousness, changing the way we approach everything from religion to artificial intelligence. Ultimately, the simulation hypothesis isn't just an abstract thought experiment. It challenges the very foundation of our understanding of existence. Whether or not we ever find definitive proof, the mere possibility forces us to question what we truly know about reality. In the next chapter, we'll explore the origins of this theory, including its roots in philosophy, and the scientific breakthroughs that have led researchers to take it seriously. Chapter 2: The Origin of the Simulation Hypothesis. Section 1: Nick Bostrom's Simulation Argument. In 2003, Swedish philosopher Nick Bostrom introduced one of the most compelling arguments for the simulation hypothesis. His paper, "Are You Living in a Computer Simulation?" presented a logical framework, suggesting that if advanced civilizations can create highly realistic simulations of conscious beings, then we are almost certainly living in one. But how does this argument actually work? Bostrom's argument is based on three key possibilities, known as the simulation trilemma. 1. No civilization ever reaches the technological level required to run advanced simulations. This could be due to self-destruction, natural disasters, or other existential threats. If this is true, then we are part of the first intelligent civilization to exist, and no simulations are being run. 2. Advanced civilizations exist, but choose not to run simulations of conscious beings. Perhaps ethical concerns, resource limitations, or other factors prevent them from creating simulated worlds. 3. Advanced civilizations create simulations, and the number of simulated beings vastly outnumbers real beings. If civilizations are capable of running high-fidelity simulations, they wouldn't just create one, they would likely create millions or even billions. In that case, the vast majority of conscious beings would exist inside simulations, rather than in the original, base reality. If this is true, then statistically speaking, we are almost certainly in a simulation. The power of Bostrom's argument comes from its simplicity. If option 3 is true, then our reality is not unique. It is just one of countless simulated worlds. Some experts have compared this idea to a nested simulation, where simulated beings create their own simulations, forming an endless chain of digital realities. Bostrom's theory gained widespread attention, not just in academic circles, but also among tech leaders like Elon Musk. Musk famously stated that the probability of us being in base reality is 1 in billions. The rapid advancement of artificial intelligence, quantum computing, and virtual reality only makes the idea seem more plausible. If we are already developing technologies capable of creating realistic digital worlds, then a far more advanced civilization could have done the same on an unimaginable scale. Of course, not everyone agrees with Bostrom's logic. Critics argue that his hypothesis, while mathematically sound, is impossible to prove or disprove. Some scientists also question whether a simulated consciousness could ever be truly self-aware. But despite the skepticism, Bostrom's argument remains one of the most influential and widely discussed theories in modern philosophy. In the next section, we'll explore how ideas similar to the simulation hypothesis have existed for thousands of years, from Plato's allegory of the cave to modern science fiction. Section 2: Historical parallels Plato to sci-fi. The idea that our reality might not be what it seems is not new. Long before the advent of computers and virtual reality, philosophers and storytellers have questioned whether the world we experience is real or just an illusion. From ancient Greece to modern science fiction, the simulation hypothesis has deep roots in human thought. One of the earliest and most famous examples of this idea comes from Plato's allegory of the cave, written over 2,000 years ago. In this story, prisoners are chained inside a dark cave, facing a wall. Behind them, a fire casts shadows of objects, which they mistake for reality. Since they have never seen the real world outside the cave, they assume the shadows are the only true existence. But when one prisoner escapes and sees the real world for the first time, he realizes that everything he once believed was just an illusion. Plato used this allegory to explore the concept of knowledge and perception. But many modern thinkers see it as an early version of the simulation hypothesis. If our senses are limited, how can we be sure that the world we perceive is the real one? Fast forward to the 17th century, and we find another influential thinker questioning reality, René Descartes. In his famous work Meditations on First Philosophy, Descartes proposed the idea of an evil demon that could be deceiving us, making us believe in a false reality. His famous phrase, "I think, therefore I am," was his way of proving that even if everything else is an illusion, at least his own consciousness must be real. Today, many compare Descartes' thought experiment to the modern idea of a simulated universe, controlled by an external intelligence. In the 20th century, the rise of science fiction introduced new ways to explore the idea of simulated realities. One of the most well-known examples is The Matrix, a 1999 film in which humans unknowingly live inside a computer-generated world. The movie's concept of waking up from an illusion echoes both Plato's cave and Descartes' philosophy. But even before The Matrix, authors like Philip K. Dick had already explored the idea that reality might be an artificial construct. His novel Ubik and the story that inspired Total Recall both question whether human experiences can be manipulated or programmed. Today, with the rise of virtual reality and artificial intelligence, these ideas no longer seem like mere philosophy or fiction. We are now capable of creating digital worlds that are increasingly difficult to distinguish from reality. If humans can do this, what's stopping a more advanced civilization from having already done the same on a much larger scale? In the next section, we'll explore how technological advancements, especially in artificial intelligence and computing power, are bringing the simulation hypothesis closer to reality. Section 3. How technology brings this closer to reality. For centuries, the idea that reality could be an illusion remained purely philosophical, but in recent decades, rapid technological advancements have brought the simulation hypothesis into the realm of serious scientific discussion. Artificial intelligence, quantum computing, and virtual reality are making it increasingly difficult to dismiss the possibility that we might already be living in a highly advanced simulation. One of the most striking examples of this is virtual reality, VR and augmented reality AR. Just a few decades ago, digital environments were limited to simple, pixelated graphics. Today, we have immersive VR experiences that can trick our brains into believing we are in a completely different world. With the right technology, a VR headset can make you feel like you are walking on Mars or standing at the edge of a skyscraper. Now, imagine what VR might look like in 100 or 1,000 years. If we can already create convincing digital experiences, what's stopping an advanced civilization from building an entire simulated universe? Then there's artificial intelligence (AI). AI has advanced to the point where chatbots can hold realistic conversations, and deep learning systems can create highly detailed digital environments. But what happens when AI becomes so sophisticated that it can simulate human-like consciousness? If a future AI system could create intelligent digital beings, those beings would have no way of knowing whether they were real or simulated. This idea directly ties into Nick Bostrom's argument that simulated consciousness may be indistinguishable from real consciousness. Another major factor supporting the simulation hypothesis is the increasing power of quantum computing. Traditional computers process information in binary ones and zeros, but quantum computers operate on an entirely different level, using qubits that can exist in multiple states at once. Some physicists believe that the strange behavior of quantum mechanics, like wave-function collapse and quantum entanglement, could be evidence that reality itself is a computational process. If the universe behaves like a quantum computer, then it might actually be running on one. Interestingly, some scientists are already searching for signs that our universe has computational limits, just like video games have rendering limits. Some physicists speculate that the universe might have a resolution, or a smallest possible unit of space and time, similar to pixels in a digital image. This idea is supported by the Planck length, the smallest measurable unit in physics. If space and time are not continuous, but instead composed of discrete units, this could indicate that we are inside a programmed simulation. What does all of this mean? It means that what was once just an abstract idea is now being investigated with real scientific methods. We may not have proof that we are living in a simulation, but the more our technology advances, the more this theory starts to look like a genuine possibility. In the next chapter, we'll dive into the scientific evidence that suggests our universe may be a digital construct. Could there be detectable glitches in reality? Are there patterns in physics that hint at artificial design? Let's find out. Chapter 3: The Scientific Evidence Clues in Physics and Mathematics. Section 1: The Universe as Code. Theoretical Hints. Imagine you're playing a highly realistic video game. The world around you looks natural, but behind the scenes, everything is controlled by lines of code. What if our own universe operates in the same way? Some scientists believe that our reality might not be purely physical, but instead follows rules that resemble a computer program. One of the biggest clues comes from mathematics. The universe is incredibly mathematical, so much so that some physicists question whether mathematics is simply a human tool, or if reality itself is built from mathematical structures. The famous physicist Max Tegmark argues that the mathematical precision of the universe suggests it could be a programmed simulation. He proposes that if everything in the universe follows mathematical laws, then reality might be nothing more than a highly sophisticated computational process. Another strange clue comes from digital physics, an emerging field that suggests the universe may not be continuous, but instead operates on discrete units, like pixels in a video game. In digital simulations, everything is broken down into tiny bits of information, and some scientists believe that our reality might work in a similar way. The Planck length, the smallest measurable unit of space, has led some researchers to speculate that space itself could be pixelated. If true, this would mean that the universe has a fundamental resolution, just like a digital screen. theoretical physicist James Gates discovered another strange mathematical pattern in the universe, something called error-correcting codes embedded in the equations of supersymmetry. These codes are similar to those used in modern computer programs to detect and fix errors. But why would the fundamental laws of the universe contain something that resembles the debugging mechanisms of computer science? Could it be that our reality is running on some kind of cosmic software? Even Albert Einstein's theory of relativity hints at a programmed reality. His equations suggest that space and time are not absolute, but can be manipulated, stretched, or compressed, just like variables in a simulation. Some scientists wonder if the speed of light limit might be similar to a processing speed cap in a computer. If our universe were a simulation, it would need built-in constraints to prevent overloading the system, just as modern video games have limits on rendering distances and frame rates. All of these clues don't directly prove that we're in a simulation, but they do raise an intriguing possibility. If the universe behaves like a digital system, could it actually be one? If reality is indeed coded, then somewhere, there must be a programmer. In the next section, we'll explore one of the most compelling pieces of evidence for a simulated universe: the mysterious Planck length and the idea of a pixelated reality. Could this be the key to unlocking the truth about our existence? Section 2: Planck length and reality's pixelation. When we look around, reality appears smooth and continuous. Space seems to flow without interruption, and time moves forward in a seamless stream. But what if this is just an illusion? Some scientists believe that, at the smallest scales, space and time might not be continuous at all. Instead, they could be made up of tiny, discrete units, like pixels on a screen. At the heart of this idea is the Planck length, the smallest possible unit of space. It measures about 1.6 times 10 to the power of negative 35 meters. An unimaginably small scale beyond anything we can directly observe. According to quantum mechanics, this is the limit at which space itself loses its smoothness and begins to behave more like a digital structure. If the universe is truly pixelated at this level, it would mean that reality has a fundamental resolution, just like a computer-generated simulation. But why is the Planck length important? One reason is that it represents a boundary beyond which our current understanding of physics breaks down. When scientists try to describe what happens at scales smaller than the Planck length, the equations of general relativity and quantum mechanics no longer make sense. This suggests that something fundamental changes at this scale, perhaps because we are reaching the smallest building blocks of reality itself. Some researchers speculate that this could be evidence that the universe is running on a kind of digital framework. In a computer simulation, everything is made up of discrete bits of data, and there is always a smallest possible unit of measurement, the resolution limit of the simulation. If our universe operates in the same way, the Planck length could be that limit. Another interesting clue comes from experiments in high-energy physics. Scientists have noticed that, when particles are accelerated to extremely high speeds, their behavior sometimes resembles the limitations seen in digital systems. Certain experiments suggest that space might have a built-in grid structure, preventing particles from moving freely at the smallest scales. This is exactly what we would expect if reality were pixelated, just like a digital image. But if space is pixelated, what about time? Some scientists believe that time itself might not be a smooth flow, but instead consists of discrete moments, jumping from one instant to the next in tiny increments. This idea, called quantized time, would mean that the past, present, and future are like individual frames in a video game, refreshing at an unimaginably fast speed. If this is true, it could be one of the strongest hints that our universe isn't an analog reality but a digital simulation. It would mean that, rather than being an infinite continuum, space and time are constructed from a finite number of data points, just like the digital worlds we create in computers. In the next section, we'll explore how mathematical structures found in physics further support the idea that our universe could be a programmed system. Could the language of the cosmos be written in code? Let's find out. Section 3. The mathematical language of nature. The deeper we look into the universe, the more it appears to be governed by precise mathematical rules. From the motion of planets to the structure of atoms, everything in nature seems to follow strict formulas, as if reality itself were built upon a mathematical framework. Could this be evidence that we are living inside a programmed simulation? One of the most striking examples of mathematics in nature is the Fibonacci sequence, a series of numbers where each term is the sum of the two preceding ones: 1, 2, 3, 5, 8, 13. This pattern appears everywhere, from the arrangement of sunflower seeds to the spiral shapes of galaxies. Why does nature consistently follow mathematical principles that seem almost too perfect? If the universe were a simulation, it would make sense for it to be based on mathematical structures, just like a computer-generated world. Another intriguing clue comes from fractals, complex geometric patterns that repeat at different scales. One famous example is the Mandelbrot set, a mathematical formula that generates infinitely detailed structures. Fractals appear throughout nature, from the branching of trees to the structure of lungs and river networks. The fact that nature follows fractal geometry so precisely suggests that reality itself might be governed by an underlying code. Much like how digital graphics use algorithms to generate complex patterns. But perhaps the most compelling evidence comes from fundamental physics. The equations that describe reality, such as Einstein's field equations for gravity or Schrödinger's equation in quantum mechanics, are written in pure mathematics. Theoretical physicist Eugene Wigner famously called this the unreasonable effectiveness of mathematics. Why does the universe, at every level, behave in ways that can be perfectly described by numbers and formulas? If we were inside a simulation, this would make perfect sense. Just like how a video game runs on a mathematical code that defines how objects move and interact. Then there's the strange discovery made by physicist James Gates, who found error-correcting codes hidden in the equations of supersymmetry. These are the same types of codes used in modern computer programming to detect and correct errors in data transmission. But why would such a system exist in the fundamental laws of physics? Could it be that our reality is not just mathematical, but computational? Some researchers believe that the universe might be built on binary information. Much like a computer program, quantum mechanics suggests that particles don't have definite states until they are observed. Similar to how pixels in a video game only render when they come into view. This idea, known as the holographic principle, suggests that everything we experience might actually be encoded on a lower dimensional surface, much like a hologram or a data storage system. If true, this would be one of the strongest indications that our universe is not a naturally occurring phenomenon, but rather a designed and programmed system. The more we study physics, the more it seems like reality operates with the precision of a highly sophisticated algorithm. In the next chapter, we'll dive deeper into computational limits in the universe. Could there be hard boundaries in physics that hint at the processing limits of a simulated world? Let's find out. Chapter 4: Computational Limits. Could our universe be running on a supercomputer? Section 1: Energy Constraints and the Simulation's Power Source. If our universe is a simulation, then it must be running on some kind of advanced computational system. But even the most powerful computers have limits. Could there be signs in our universe that suggest we are running up against the constraints of an underlying computational process? One major clue lies in the energy limits of the universe. Every computational system requires energy to process information. If the universe were a simulation, we might expect to see evidence of processing constraints, just like how a video game has a maximum rendering capacity before it starts to lag. Some scientists believe that the speed of light might be one such limit. In physics, nothing can travel faster than light. But why does this speed exist? If the universe were being simulated, this could be a built-in processing cap, ensuring that information can only be updated at a maximum rate, preventing computational overload. Another interesting consideration is the Bekenstein bound, a theoretical limit on the amount of information that can be stored within a given volume of space. This principle suggests that there is a maximum amount of data that any region of the universe can contain, similar to the memory constraints of a computer system. If our universe has a finite amount of information it can process, it might be evidence that we are inside a simulated environment with restricted computational resources. Then there's the question of entropy and information loss. In physics, the second law of thermodynamics states that entropy, or disorder, always increases over time. However, if the universe were a simulation, entropy might simply be a way to manage computational efficiency. Instead of an infinite universe, what if we are in a system that periodically resets or optimizes itself? Much like how computers compress and organize data to free up memory. Some researchers have even suggested that black holes might act as information storage or compression systems, preventing data overload in the simulation. Additionally, some scientists have considered whether quantum mechanics itself hints at a computational limit. In quantum systems, particles exist in multiple states until they are observed, an idea that closely resembles lazy loading in computer science, where digital objects are only rendered when they are needed to save processing power. If the universe were a simulation, it would make sense for it to function in a way that optimizes efficiency, only calculating details when they become necessary. These computational constraints suggest that, if our universe is a simulation, it may not be infinite. Instead, it could be operating within a limited processing environment, designed by an external intelligence with a set amount of computational resources. In the next section, we'll explore another strange limitation in physics: black holes and their role in storing information. Could black holes act as data processors in a simulated universe? Let's investigate. Section 2: Black holes and information storage. Black holes have long been a source of mystery in physics. These cosmic giants have such intense gravitational pull that nothing, not even light, can escape their grasp. But beyond their mind-bending effects on space and time, black holes may hold an even deeper secret. They could be key components in a simulated universe, acting as massive data storage or processing units. One of the most intriguing discoveries in modern physics is the holographic principle, a theory suggesting that all the information within a black hole is stored on its surface, rather than inside it. This idea was proposed by physicist Gerard T. Hooft, and later expanded by Leonard Susskind. According to this principle, the three-dimensional information of an object that falls into a black hole is somehow encoded on its two-dimensional event horizon, just like how holograms encode 3D images on a flat surface. But what does this have to do with the simulation hypothesis? If information in the universe behaves like it does in a black hole, it could mean that reality itself is holographic, essentially a projection of encoded data, similar to how a simulation operates. This would imply that what we perceive as a three-dimensional world is actually being stored and processed in a lower dimensional system, just like data on a computer chip. Another major breakthrough came from Stephen Hawking, who discovered that black holes aren't completely black, they slowly emit radiation, now known as Hawking radiation. But this led to a paradox. If black holes lose mass over time by emitting radiation, what happens to the information stored inside them? According to quantum mechanics, information should never be lost. Yet black holes appeared to violate this principle. This puzzle, known as the black hole information paradox, has led scientists to consider the possibility that black holes act like cosmic data processors, preserving and redistributing information in ways we don't yet understand. Some physicists, including Juan Maldacena, have suggested that black holes could be quantum computers, processing information at the most fundamental level of reality. If black holes function like information storage units, it raises an even more provocative question. Could they be part of the underlying computational system running our universe? In other words, if the universe is a simulation, black holes might serve as high-capacity data banks, managing and recycling information across different regions of space-time. Additionally, some researchers have proposed that the entire universe might behave like a black hole, with all the information of existence encoded on a vast cosmic horizon. If this is true, then our reality may be nothing more than an elaborate information structure, operating under the constraints of a computational system, far beyond our current understanding. In the next section, we'll explore another groundbreaking idea, the holographic principle, and whether our entire universe might be a projection of data, rather than a true physical entity. Could this be the ultimate proof that we are living in a simulation? Let's find out. Section 3. The holographic principle. Are we in a 2D projection? What if everything we see, hear, and touch is just a projection? An illusion created by an underlying information structure? It may sound like science fiction, but some of the world's leading physicists believe that our universe might actually be holographic, meaning that our three-dimensional reality is encoded on a two-dimensional surface. If true, this could be one of the strongest pieces of evidence that we are living in a simulation. The holographic principle was first proposed by physicist Gerard T. Hooft, and later expanded by Leonard Susskind. The idea is based on black holes and the way they store information. As we discussed in the previous section, when an object falls into a black hole, its information doesn't disappear. Instead, it is preserved on the event horizon, the two-dimensional surface surrounding the black hole. This led physicists to wonder, if black holes can store three-dimensional information on a two-dimensional surface, could the entire universe work the same way? In other words, everything we experience, space, time, and matter, could be the result of a deeper, lower-dimensional reality. Just like a hologram contains a 3D image encoded in a 2D surface. Our universe might be a 3D projection of fundamental information stored on a distant boundary. One of the most fascinating aspects of this theory is that it aligns with some of the strangest discoveries in modern physics. For example, in string theory, one of the most promising theories of everything, researchers have found that equations describing gravitational interactions in 3 dimensions can be rewritten as quantum equations in 2 dimensions. This suggests that gravity and space-time itself might be emergent properties, arising from a more fundamental layer of reality. But what does this have to do with the simulation hypothesis? If our universe is a hologram, it would mean that everything we perceive as physical is actually just encoded information. This is exactly how computer simulations work. In a video game, characters and objects appear to exist in a 3D space, but they are actually generated by a 2D screen displaying pre-programmed data. If the universe functions in a similar way, it could mean that we are living in a computed or simulated reality. Some scientists believe we might already have evidence of this. In 2017, researchers at the Fermi National Accelerator Laboratory, Fermilab, conducted an experiment called the holometer, designed to detect quantum-scale fluctuations in space-time. Their goal was to see if space-time itself is pixelated at the smallest scales, just like a holographic display. While the results remain inconclusive, the experiment represents a serious attempt to test whether reality has a digital foundation. If the holographic principle is correct, then our reality is not what it seems. It would suggest that everything we experience is simply an illusion, a projection of deeper, encoded data. This would be one of the strongest arguments, yet, that our universe is not a natural phenomenon, but a carefully designed system operating under strict computational rules. In the next chapter, we'll explore quantum mechanics and the observer effect, one of the strangest and most mysterious aspects of reality. Could the fact that reality only renders when observed be another clue that we are in a simulation? Let's dive in. Chapter 5: Quantum Mechanics and the Observer Effect. Section 1: The Double-Slit Experiment's Strange Implications. One of the most bizarre and unsettling discoveries in modern physics is that reality seems to change depending on whether or not it is being observed. This phenomenon, known as the observer effect, was first demonstrated in a famous experiment called the double-slit experiment. An experiment so strange that even Albert Einstein struggled to accept its implications. But could this be more than just a weird quirk of quantum mechanics? Could it actually be evidence that our universe is a simulation, rendering itself only when observed? The double-slit experiment is surprisingly simple. Imagine you have a barrier with 2 narrow slits and a screen behind it. If you shoot tiny particles, like electrons or photons, toward the slits, you would expect them to pass through one or the other and create 2 lines on the screen. That's how normal objects behave. But when scientists performed this experiment at the quantum level, something inexplicable happened. Instead of forming 2 distinct lines, the particles formed a complex interference pattern, as if they had behaved like waves and passed through both slits at the same time. This is known as wave-particle duality, the idea that quantum particles can act both as waves and as particles, depending on the situation. The real mystery begins when scientists try to observe the particles directly. When a measuring device is placed at the slits to determine which path each particle takes, the interference pattern disappears, and the particles suddenly behave as if they only went through one slit, like classical objects. In other words, The mere act of observation changes the outcome of the experiment. But what does this mean? Why should particles behave differently when they are being watched? Some physicists argue that this suggests consciousness plays a role in shaping reality. A deeply unsettling idea that challenges everything we assume about the nature of existence. One explanation is that reality might be rendered on demand. Much like how video games only generate graphics when a player is looking at a particular area. If a game had to render the entire world at full resolution all the time, it would require enormous processing power. Instead, games use a technique called lazy loading, where only the parts of the world that the player is interacting with are generated in real time. Could the universe work the same way? If we are in a simulation, it would make sense for reality to only be fully calculated when it is being observed. This would explain the strange behavior of quantum particles. They only decide on a definite state when measured. Just as a video game environment only loads when needed. Even physicists like John Archibald Wheeler have suggested that reality might be a participatory universe, where the act of observing helps bring reality into existence. If this is true, then our consciousness is not just a passive experience of the world. It might actually be playing a role in shaping it. In the next section, we'll explore an even deeper mystery: quantum entanglement and the strange way information seems to travel faster than the speed of light. Could this be another sign that we are living in a programmed universe? Let's investigate. Section 2: Quantum entanglement and the limits of reality. Imagine two particles that are separated by billions of light years. Now, what if changing the state of one particle instantly affected the other? No matter how far apart they are. This bizarre phenomenon is called quantum entanglement, and it is one of the strangest mysteries in physics. Some scientists believe it could be a key clue that our universe is not what it seems. Could it be evidence that we are living inside a simulated reality, where information isn't bound by physical space? What is quantum entanglement? Quantum entanglement occurs when two or more particles become linked in such a way that their states remain connected, even when separated by vast distances. When one entangled particle is measured, its partner instantaneously takes on a corresponding state, faster than the speed of light. This effect was so puzzling that Albert Einstein famously called it spooky action at a distance. This phenomenon directly contradicts one of the fundamental principles of physics, that no information can travel faster than the speed of light. If entangled particles are truly communicating instantly, then it suggests that either 1. Our understanding of space-time is incomplete, or 2. Information is being exchanged outside the normal limits of physics, perhaps through an underlying computational system. The simulation connection. If our universe is a simulation, quantum entanglement could be one of the strongest hints. In a well-designed computer program, distant objects don't need to communicate through physical space. They simply share the same underlying data. Think about how a video game works. When a player moves an object in the game, the change happens instantly because the game's physics engine updates all relevant data at once. Some researchers believe that entanglement might work in a similar way. Instead of particles transmitting information across space, they could simply be updating their states simultaneously, in response to a deeper computational framework. This would mean that what we perceive as reality is actually just a layer of information processing happening beneath our level of awareness. Scientific tests and the no hidden variables theorem. Over the years, scientists have tried to prove whether entangled particles really influence each other instantly, or if there is some hidden process at play. The most famous test is called Bell's theorem, which showed that no classical or hidden variable explanation could account for quantum entanglement. In other words, the effect is real, and it cannot be explained using traditional physics. Recent experiments have confirmed entanglement's reality with even greater precision. In 2015, scientists conducted an experiment where entangled photons, light particles, were measured at a distance, and the results strongly supported the idea that entanglement happens instantaneously, without any signal traveling between the particles. This has led some researchers to ask, is the universe fundamentally connected by an invisible data structure? What this means for reality, if quantum entanglement is more than just a weird quirk of physics. It could mean that space and time themselves are not fundamental. They might just be convenient illusions created by a deeper system. Some physicists, like Juan Maldacena, have proposed that entanglement could be the key to understanding the true nature of reality. According to this view, the universe might be a vast network of entangled information, operating outside the limits of space-time. If that's true, it would strongly support the idea that we are inside a computational system, a kind of digital reality, where everything is connected through an unseen information framework. In the next section, we'll explore another mind-boggling idea. Does human consciousness itself play a role in shaping this simulation? Could our thoughts and awareness be part of the underlying code that drives reality? Let's find out. Section 3. Does consciousness influence the universe? If the universe is a simulation, then who, or what, is running it? Could our own consciousness play a role in shaping reality? Some scientists and philosophers believe that consciousness itself might be the key to understanding the simulation hypothesis. One of the biggest mysteries in physics is why quantum particles don't take on definite states until they are observed. As seen in the double-slit experiment, particles exist in multiple possibilities until someone measures them. This has led some researchers to propose a radical idea. Consciousness might be what renders reality into existence, just like how a computer game only generates graphics when a player looks at a scene. The famous Wheeler's delayed choice experiment supports this idea. It suggests that decisions made in the present can retroactively affect past events. At the quantum level, this raises a disturbing possibility. Does reality exist independently of observation? Or does our awareness actively shape it? Some physicists, like John von Neumann, suggested that the human mind might be a fundamental part of reality itself. If consciousness is required to collapse quantum possibilities into actual outcomes, it could mean that reality is not just being computed externally. It may be interactive, responding to observers in real time. This could have profound implications for the simulation hypothesis. If reality is designed to change based on observation, it would suggest an intelligent system behind the scenes, adapting to our awareness. This is exactly how simulations and artificial worlds are programmed, to only process what is necessary when needed. But if consciousness plays a role in shaping the universe, it leads to even deeper questions. Are we just passive observers? Or are we participants in an evolving simulation? And if our thoughts can influence reality, does that mean we have more control over this world than we think? In the next chapter, we'll explore a crucial question. Could we actually detect evidence of the simulation? If we are inside a programmed universe, are there glitches or clues hidden in physics that reveal the truth? Let's find out. Chapter 6. Could we detect the simulation? Section 1. Searching for glitches, cosmic errors in reality. If we are living in a simulation, could we find glitches in reality? Small errors that hint at the artificial nature of the universe. Just like video games sometimes reveal flaws in their programming, some scientists believe there may be observable bugs in the laws of physics that suggest our world is not what it seems. One possible clue comes from cosmic rays, high-energy particles that travel through space at nearly the speed of light. When physicists study these particles, they sometimes encounter a strange problem. Some cosmic rays seem to have more energy than should be possible under the known laws of physics. This has led some researchers to speculate that these anomalies could be evidence of computational errors, like an overloaded system struggling to process extreme values. If the universe has a limit to how much energy it can simulate, these cosmic rays might be pushing up against that boundary. Another potential sign of a simulated universe is the discretization of space and time. If reality were truly continuous, then measurements at the smallest scales should show smooth transitions. However, some experiments suggest that space itself might be pixelated at the Planck scale, similar to how a digital image consists of tiny pixels rather than a perfect flow of color. If true, this could indicate that the universe is running on a finite computational grid. Much like a simulation, some scientists have also pointed to strange inconsistencies in physics, such as the unexplained nature of dark matter and dark energy. These mysterious forces make up 95% of the universe, yet scientists have no direct way to observe them. Could they be artifacts of an imperfectly designed simulation? If an advanced civilization were running a large-scale simulation, they might have created shortcuts or simplified models to handle large-scale cosmic structures efficiently. Just like how video games use background rendering to avoid processing unnecessary details. Perhaps the most famous idea comes from simulation constraint theories, which propose that certain laws of physics might be deliberately designed to prevent us from uncovering the truth. For example, the speed of light limit might function like a processing speed cap, ensuring that no information travels faster than what the system can compute. Similarly, the uncertainty principle in quantum mechanics might be a built-in feature that prevents us from examining reality too closely, much like how digital images become pixelated when zoomed in too far. If these glitches are real, they could be the strongest hints that we are inside a simulation. But how could we test this theory further? In the next section, we'll explore how scientists are using high-energy cosmic rays to look for actual proof of a simulated universe. Could we be on the verge of discovering the truth? Let's find out. Section 2. High-energy cosmic rays and their strange behavior. If the universe is a simulation, then there should be limits to its processing power. Just like any computer system, some scientists believe that we might already be seeing signs of these limitations. In high-energy cosmic rays, mysterious particles that travel through space at incredible speeds, could these particles be revealing the underlying code of our reality? Cosmic rays are extremely energetic, subatomic particles that originate from deep space, possibly from supernovae, black holes, or other unknown cosmic phenomena. When they reach Earth's atmosphere, they collide with air molecules, creating a cascade of secondary particles. Most cosmic rays follow well-understood physical laws, but some exhibit anomalous energy levels so high that they seemingly violate the known rules of physics. One of the strangest discoveries in this field came from the Bryson-Zatsepin-Kuzmin GZK limit. This theoretical limit suggests that cosmic rays, traveling across vast cosmic distances, should lose energy due to interactions with background radiation. However, scientists have observed ultra-high energy cosmic rays, UHECRs, that appear to exceed this limit, defying expectations. Why is this important? If we assume the universe is a simulation, then such energy anomalies could represent a breakdown in the system's calculations. In a simulated world, there might be an upper energy threshold, beyond which the system can no longer correctly process data, leading to unexpected behaviors, just like how digital graphics sometimes glitch when overloaded with too much detail. Another possible explanation is that these particles are interacting with hidden dimensions, or structures beyond our standard model of physics. If the universe is a simulation, then what we perceive as extra dimensions might actually be data layers within the computational framework, influencing how particles behave. Scientists are actively investigating these anomalies through experiments, like the Pierre Auger Observatory and NASA's space-based cosmic ray detectors. If they find a pattern in these ultra-high energy cosmic rays that cannot be explained by conventional physics, it might be a major clue that reality has computational constraints, just like a simulation would. In the next section, we'll discuss another key challenge: the limits of scientific testing. If the universe is a simulation, would we even be able to prove it? Or are we trapped inside a system that prevents us from discovering the truth? Let's explore this final mystery. Section 3: The limits of scientific inquiry. If we truly live in a simulation, then one question becomes unavoidable. Can we ever prove it? Could there be a fundamental limit to what we can discover, one deliberately imposed to prevent us from realizing the truth? Many scientists believe that even if the universe is a simulation, we may never be able to confirm it with certainty. This is because any test we devise would still be conducted within the simulation itself. Imagine a character in a video game trying to prove that their world is artificial. They can only interact with the game's physics and rules, never stepping outside the system. The same might be true for us. One major obstacle is the observer effect. As we've seen with quantum mechanics, reality seems to change, depending on how we observe it. If our universe is a simulation, then the very act of trying to measure it might alter the results. Just like how code in a computer program can be designed to self-correct when examined too closely. Some scientists suggest that the fundamental randomness in quantum mechanics might actually be a security feature, preventing us from hacking the system. Another challenge is computational limits. If the universe is running on a vast but finite processing system, then it might have built-in restrictions to keep us from overloading it. Concepts like the speed of light, the Planck length, and the uncertainty principle might not just be natural laws. They could be artificial constraints, preventing us from accessing deeper layers of reality. Some have even speculated that advanced civilizations running the simulation might have fail-safe mechanisms in place. If we ever got too close to uncovering the truth, the system could reset itself or alter our perceptions to make us forget what we've discovered. This might explain why the simulation hypothesis, despite its logical appeal, remains so difficult to test scientifically. Despite these challenges, researchers continue to explore ways to detect potential glitches or computational patterns in reality, whether through quantum mechanics, cosmic rays, or deep space observations. The search for evidence of a simulated universe is ongoing. But what if we did prove we are in a simulation? What would that mean for humanity? In the next chapter, we'll explore the philosophical and ethical consequences of discovering that our reality is not what it seems. Would this knowledge change the way we live? And if we are in a simulation, should we try to escape it or embrace it? Chapter 7. What if we are in a simulation? Section 1. Ethical and philosophical consequences. If we could prove that our universe is a simulation, what would that mean for humanity? Would it change the way we live, think, and interact with the world? The idea that our reality is an artificial construct raises profound ethical and philosophical questions. Ones that challenge everything we assume about existence. One of the biggest concerns is free will. If the universe is simulated, does that mean our choices are pre-programmed? Are we simply running on a set of predefined rules, like characters in a computer game? Some scientists and philosophers argue that even in a simulation, we can still experience real emotions, thoughts, and decisions, just as AI in a video game can appear to act independently within its programmed environment. But if our actions are influenced or controlled by an external intelligence, does that diminish our sense of personal responsibility? Then there's the question of the creators. If the universe is simulated, who, or what, is running it? Part of an advanced experiment? A form of entertainment? Or could we be inside a vast training program designed for future civilizations? Some researchers have compared this idea to a sandbox simulation, where an advanced species might be observing how intelligent beings develop under different conditions. If so, what happens when we finally realize the truth? Would the creators intervene, or even shut down the simulation? This leads to another unsettling possibility. Are we alone? If we are inside a simulation, then perhaps the reason we haven't encountered intelligent alien civilizations is that they were never programmed into our reality. The so-called Great Silence of the universe might not be a coincidence. It could be a deliberate design choice. If our world is nothing more than a constructed experiment, then the absence of extraterrestrial life might not be because it doesn't exist, but because it was never written into the code. On the other hand, some see the simulation hypothesis as a positive revelation. If reality is designed, then perhaps it has a purpose. Religions and spiritual traditions have long suggested that the universe is created by an intelligent force. A simulated reality could be seen as a modern, technological version of this idea, where an advanced intelligence, rather than a deity, has shaped our existence. Another ethical dilemma arises when we consider what happens next. If we confirm that we are in a simulation, should we try to escape it? Some might argue that we should attempt to communicate with the creators, if they exist. Others believe that tampering with the simulation could be dangerous, potentially triggering a reset or shutdown. If our world is dependent on an external system, then disturbing that system could lead to unpredictable consequences. Ultimately, whether we are in a simulation or not, our experiences still feel real to us, just as characters in a novel or a video game perceive their world as genuine. We, too, live within the framework provided to us. Perhaps the real question is not whether we are in a simulation, but how we choose to live within it. In the next section, we'll explore an even more fascinating question. What would happen if we actually discovered the truth? If humanity found undeniable proof of the simulation, how would society react? Let's investigate. Section 2. What would happen if we discovered the truth? What if one day, scientists found undeniable proof that we are living in a simulation. How would society react? Would it lead to a new era of understanding, or cause chaos and uncertainty? The discovery of such a fundamental truth would have profound effects on science, religion, and the way we perceive our very existence. First, let's consider the scientific impact. If we confirm that our universe is simulated, it would mean that physics is not the ultimate truth, but rather a set of rules designed by an external intelligence. Scientists would shift their focus from understanding natural laws to deciphering the code of reality. Instead of asking what the universe is made of, researchers might start investigating who or what created it, and whether it can be manipulated. It could open the door to breakthroughs in computing, artificial intelligence, and even the possibility of hacking reality itself. Next, there's the philosophical and religious impact. Many religions already propose that the universe was created by a higher power. If we found proof of a simulated reality, some might see it as confirmation of intelligent design, while others could struggle to reconcile their beliefs with the idea of an artificial universe. Would the creators be seen as gods, or simply as advanced beings running an experiment? The nature of faith and spirituality could change dramatically. But what about society as a whole? Some people might embrace the knowledge, seeing it as an opportunity to better understand existence. Others, however, could react with fear or nihilism, believing that life has no meaning if we are just part of a program. Would governments try to suppress this information to prevent mass panic? If the discovery became public, it could spark a wave of philosophical movements, some aiming to escape the simulation, others choosing to accept it and live fully within its boundaries. And then there's the biggest question of all: what if the creators of the simulation noticed that we had discovered the truth? If they were observing us, would they react? Would they reveal themselves, change the program, or even shut it down? If the simulation were just an experiment, reaching this level of awareness might mean we have reached the end of the test. Ultimately, whether or not we are in a simulation, the search for truth is what defines us as intelligent beings. Perhaps the real lesson is not whether our world is real or artificial, but what we choose to do with the knowledge we gain. In the next section, we'll explore how this theory changes our perspective on life. If reality is just a simulation, does that change the way we live, love, and experience the world? Let's find out. Section 3. How this theory changes our perspective on life. If we are living in a simulation, does it change the way we experience life? Should we see our existence differently? Or does it even matter at all? While the simulation hypothesis challenges our understanding of reality, it also offers a unique perspective on how we choose to live our lives. One of the most profound realizations is that our world may be designed for a purpose. If an advanced intelligence created this reality, then perhaps our existence is not random. Whether we are part of an experiment, a simulation for entertainment, or a training ground for something greater. This idea gives a sense of meaning to our lives. Instead of feeling like insignificant specks in an endless cosmos, we might be part of a grand design, one that we have yet to fully understand. This perspective also encourages curiosity and exploration. If we are inside a system with hidden rules and structures, then understanding those rules becomes one of the most important pursuits. Just as scientists study the physical world to uncover its secrets, the simulation hypothesis suggests that we should seek to understand the deeper code of reality. What if there are ways to access hidden aspects of the simulation? Could we learn to manipulate it, just as programmers manipulate computer systems? But what about personal meaning? If life is a simulation, does that make our emotions, relationships, and experiences any less real? Not necessarily. Even in a simulated world, what we feel is real to us. Just like a character in a novel experiences joy, pain, and love within their own story, we, too, experience genuine emotions within our reality. Whether the universe is made of atoms or data, our lives and interactions still have value and significance. Some take this idea further and suggest that if reality is a simulation, then perhaps we should embrace it like a game. Instead of worrying about existential questions, we could focus on making the most of our time here, seeking adventure, pushing boundaries, and creating the best possible experiences. If this world is a designed system, then maybe the goal is not to escape it, but to play it well. In the end, whether we are in a simulation or not, the choices we make still define our reality. The way we treat others, the way we seek knowledge, and the way we experience life all remain deeply meaningful. Perhaps the greatest lesson of the simulation hypothesis is that reality is what we make of it, whether it's programmed or not. If you found this video helpful or interesting, please give it a thumbs up and subscribe to the channel.